Welcome everyone to this edition of ZKStudyClub. I'm Alex Pruden. We have Anna Rose here as well. We're hosting today Jonathan Bootle from IBM Research and Katerina Sotiraki of UC Berkeley. And this is the paper being presented is also co-authored by Alessandro Chiesa, also from UC Berkeley. And yes, we're very excited to hear from them today about sum check arguments and their applications. So Jonathan, over to you.
Thanks very much for the introduction. So apparently I was speaking a little quietly earlier, and I also have trains going past my building. So if there's something that you didn't hear, or you just want to ask a question, then just feel free to interrupt me at any time. Okay, so yeah, the title of our paper is called Sum Check Arguments and Their Applications. And this is a paper about succinct arguments. So I don't need to tell anybody in the audience that succinct arguments have had, really massive impact in cryptography, implemented in all kinds of blockchains and, in other kinds of products these days. So in a succinct argument, the setup is that we have some kind of common statement, and there's a prover and a verifier, and the prover wants to convince the verifier that this common input actually represents a true statement. And the prover knows a witness. So in this case, the statement's like an arithmetic circuit or something like that with a specified output. And the prover wants to convince the verifier that they know a witness, which produces the desired output when you plug it into the circuit. So obviously the prover and the verifier are going to interact, exchange various messages. And then at the end of the interaction, if the verifier was convinced that the prover was really telling the truth, and we've got a true statement here, then the verifier is going to accept and otherwise reject. So we've got three different properties here that we want a succinct argument to satisfy. We've got completeness. So if the prover has a valid witness, then the verifier should always accept. We've got soundness, which means if the prover's lying and they don't have a good witness, or there's a bad common input, then the verifier should always reject. And then later on, we're going to talk about stronger soundness properties like knowledge soundness. And lastly, the thing that makes succinct arguments succinct is the fact that the messages exchanged between the prover and the verifier are much smaller than the size of the prover's witness. Otherwise, the prover could just send their witness to the verifier, and the verifier could check everything for themselves. So there'd be no advantage to the succinct argument otherwise. So now, all of the succinct arguments that we wrote about in our paper really stem from the sum check protocol, which comes from way back in 1992. So in the sum check protocol, what's common to the prover and the verifier is a polynomial P with several different variables defined over a finite field F, and then like a public value from the finite field, which is U. So Dara has just pointed out that zero knowledge is also a useful property of succinct arguments, but yeah, for the most part, we're not going to consider zero knowledge today. You can see the paper for some some other connections to zero knowledge and how we get some zero knowledge succinct arguments. But back to the sum check protocol. In the sum check protocol, we've got this publicly known polynomial and a value in a finite field. And what we have here is that the prover wants to convince the verifier that the polynomial evaluations sum up to give the value. So how this protocol goes is the prover computes various smaller polynomials, which they send to the verifier, and the verifier responds with these uniformly random challenges. And then at the end of the protocol, the verifier performs various checks on the prover's polynomials. And at the very end, the verifier can... Oh, I think I've got some feedback. At the very end of the protocol, the verifier can perform one last evaluation of the original public polynomial at a random point, and then check that this evaluation is equal to some other value that they already know. So the sum check protocol is useful for reducing the task of checking this big sum of polynomial evaluations to checking just one single polynomial evaluation, which is much cheaper. So the communication costs of the sum check protocol are the number of variables in the polynomial multiplied by the degree of the polynomial in finite field elements. And the soundness guarantee of this protocol is that if the polynomial evaluations don't sum up to the right thing, then the verifier should accept with probability proportional to like the number of variables times the degree over the size of the finite field. This is an important slide because it's this sumcheck protocol that all of the protocols in our paper are based on. So hopefully everybody's at least heard of this protocol before. So the sumcheck protocol is actually really important. It's been used in loads of different works. So it started being used, first of all in complexity theory in the 90s, and I think the first use of the sumcheck protocol was for proving that the co-MP complexity class is contained in IP, but it's been used in other probabilistic proofs too. More recently, we've got loads and loads of succinct arguments, which are usually based on the sumcheck protocol, plus some kind of extra cryptographic ingredient. So there are absolutely loads of these. And it's almost as if every new variant of the sumcheck protocol gives you new types of succinct arguments with amazing new properties. So there are univariate sumcheck-based arguments, which use a univariate sumcheck protocol, which works a bit differently and gives you like different efficiency trade-offs for the prover and the verifier. There's a sumcheck protocol for error-correcting codes instead of polynomials. And this gives you some really cool succinct zero-knowledge arguments with like great asymptotic properties. And in fact, the sumcheck protocol is just so popular and so widely used that we've got blog posts with titles like this, The Unreasonable Power of the Sumcheck Protocol by Justin Toller, which is a really great blog post, and I'd encourage you to check it out. But why is the sumcheck protocol like this popular? Just what's so good about it? Well, it's got various different useful properties. We know that the sumcheck protocol can be implemented so that the prover runs in linear time. That's linear time relative to the number of coefficients in the polynomial. Or if you link that back to a statement about circuits or something like that, linear in the number of gates in the circuit. And actually, the sumcheck protocol has another cool property. It can be implemented in really small space. So you can have a sumcheck prover, which uses a really small amount of memory via some kind of like sliding window algorithm, perhaps. And then, lastly, the sumcheck protocol is very special because you can make it non-interactive in the standard model without using random oracles, but just using some very specially designed like correlation intractable hash functions or something like that. So yeah, it's really a very special protocol. So after having seen this slide and all of the work that's based on the sumcheck protocol, you might be forgiven for thinking that it's actually the only protocol in the space of zero-knowledge arguments and succinct arguments. Well, that's not necessarily true. So there's another body of work based on what we'll call split and fold techniques. So one of the first papers on split and fold techniques appeared in 2016. And this was giving succinct arguments for arithmetic circuit satisfiability based on the discrete logarithm assumption. And based on that, there were various different like optimizations and improvements and more discrete log arguments for different kinds of things with different types of properties. But split and fold techniques are not just good in the discrete log setting. They've been generalized to work with different assumptions and different cryptographic settings like pairing groups, unknown order groups like RSA groups, and there are even some post-quantum split and fold techniques that work based on lattice assumptions. And all these split and fold techniques work in basically the same kind of way. You have a cryptographic commitment to a very long message, which gets split into a few parts, which are then combined together by taking some kind of random linear combination. So since they all work in a similar way, there are also some abstractions which try and unify all the different split and fold techniques across the different settings. Now, split and fold techniques also give you some pretty efficient succinct arguments in practice, just like some of the sumcheck-based ones. And in particular, some of the discrete log-based arguments are implemented in lots of different cryptocurrencies. Okay, so we saw why the sumcheck protocol is good. What's so good about split and fold techniques? Well, okay, just like the sumcheck protocol, you can implement most of the split and fold techniques using a linear time prover. So that's something they have in common. Yeah, similarly, there are some recent works which show how you can implement discrete log arguments based on these split and fold techniques, or based on RSA groups, using like a streaming prover that runs some kind of sliding window algorithm and uses a very small amount of memory. So that's another really nice property. And that's, well, yeah, that's also just the same as the sumcheck protocol. So you might wonder if there's something more going on here, if there's some kind of deeper connection between the two types of techniques. Okay, so yeah, spoiler alert, as I'm going to talk about our results, like, yes, there is, of course there is. In our paper, we have a look at these split and fold techniques, and we produce like a variant of the sumcheck protocol, which we call sumcheck arguments. And this basically tries to encompass most of the existing split and fold techniques, and it shows that they're like directly connected to the original sumcheck protocol. And this is really nice because it shows that these split and fold techniques, they're not really a separate body of work at all. In fact, they're really similar in spirit to the other types of succinct arguments, which are based on the sumcheck protocol. Okay, so now I'm going to talk a bit more about what sumcheck arguments actually are. So the goal of a sumcheck argument is to kind of give a type of sumcheck protocol which proves that a cryptographic commitment has an opening. So the prover wants to prove to the verifier that, given a cryptographic commitment C and some kind of commitment key CK, that the prover knows a message which is committed inside that cryptographic commitment. So our requirement here is going to be that the communication costs of the argument are much less than the length of the message. And typically, to get an efficient and highly succinct arguments for commitment openings, you want to focus on commitments with some sort of special structure. So the special structure that we're going to use so that we can incorporate these sumcheck protocols into the arguments is called the notion of like sumcheck-friendly commitments. Okay, so we're going to say a commitment scheme is sumcheck-friendly if you can take any commitment to like any message, and you can express it as like a sum of different polynomial evaluations. So let me break this definition down a bit. Like first, we'll be summing polynomials on the right-hand side over a set of evaluation points from a set H, where H is a subset of some kind of ring, or maybe a finite field. The commitment space, C, where all the commitments come from, should be a module over the same ring R. So on the right-hand side, the polynomial evaluation part is split into evaluations of a message polynomial over another R module, M, and a key polynomial over another R module, K. And then obviously these two evaluations come from different spaces. So we also incorporate some kind of combiner function to map them onto the space of commitments. Okay, so just in case this definition looks a bit like weird and scary or too abstract, I'll show you an example, which is like how to view a Pedersen commitment as a sumcheck-friendly commitment. So a Pedersen commitment is like a sum of products of like message elements from some finite field multiplied by key elements from some cryptographic group, like an elliptic curve group or something like that. So in this case, so one possible choice, there are others, but one possible way you could express Pedersen commitment as sumcheck-friendly is to choose H to be like -1 and 1. And the ring could just be like a finite field of prime order. The message space is going to be the same finite field, and the message polynomial that we're going to pick is like a multilinear polynomial. So every single element of the message appears in like exactly one coefficient of this multilinear polynomial. The key polynomial is really similar, except it's actually a polynomial over the group instead of the finite field. But again, we've got like one element of the key in each coefficient of the polynomial. And then lastly, the way you would combine these two is just like using exponentiation or like point multiplication between the finite field and the group there. Okay, so so this might seem a bit heavy. So like yeah, any questions about like sumcheck-friendly commitments or this definition?
There was a little bit of conversation in the chat around, I think this is an earlier question, is H a subgroup of F? But then there's some conversation about that not being the case.
Yeah, yeah, absolutely. So it doesn't have to be, but yeah, I think it's often useful if that's the case. Yeah, there are some nice formulae for like expressing polynomial evaluations if you're summing over like a multiplicative subgroup or something like that. So it's often useful, but not always necessary.
Where does H equals -1, 1 come from in the Peterson case?
So actually a bit later, I'm gonna talk about the protocol that you would run on this very example in a bit more detail. But to help look ahead a bit, basically summing over -1, 1, it only retains all of the monomials with like even coefficients, and we're going to be able to show that actually kind of selects all the terms in the Peterson commitment in this sum. But yeah, we're going to see some explicit formulae later. So
it'll become clear, I'm sure.
Okay. Yeah, hopefully. Thanks. Yeah. L equals n here. Okay, so if n is the length of the message as a vector, then L would be like log n. So if we have log n different variables, L equals log n different variables, and we make a multilinear polynomial, then it's going to have like n coefficients, like one for each element of the message of one for each element of the message or of the key. Okay, great. So given this notion of sumcheck-friendly commitments, I can actually move on to stating the main result in our paper. And that is that if you have a commitment scheme which is sumcheck-friendly, like on the previous slide, and also satisfies this like extra invertibility property that we'll talk about a bit more later, then if you just apply the sumcheck protocol with some small modifications to the polynomial in the middle of the slide, then you get a succinct argument of knowledge for an opening to the commitment. And this has communication costs like exactly the same as the sumcheck protocol, pretty much. So the first thing that like a really sharp observer might notice about this slide is that the original sumcheck protocol was actually, the way I wrote it down, it was all over finite fields. And this polynomial here, if you have a look, it's actually defined over the commitment space, which is some kind of weird R module and not necessarily a finite field at all. But that's actually okay because it's pretty easy to show that you can run the sumcheck protocol over like more general domains than finite fields, like different modules or polynomials over different groups. So everything extends quite easily to those cases. And for the communication costs of the sumcheck protocol, you can keep the idea in your head that this is going to turn into communication costs something like logarithmic in the length of the message. Okay, so this is just about succinct arguments for proving that the prover knows an opening to a commitment. But why don't we try and go a bit further? In lots of these prior works on split and fold techniques or these other sumcheck and polynomial commitment-based works, what people do is they reduce like various NP statements like ONCS or circuit sat to different statements about like scalar products, for example, and then they can use the sumcheck to design like efficient subroutines to let the prover and verifier reason about different scalar product relations. So in our work, we actually build on our sumcheck arguments, and we can do the same thing. So we actually have a very general sumcheck argument that lets you reason about scalar products over bilinear modules. And the idea of these bilinear modules is to capture a lot of different cryptographic settings at the same time, like all the settings that people have considered so far for these split and fold techniques. So using our scalar product argument in this general setting as like a subroutine, then we can get like quite general succinct arguments for different types of NP statements. So what we'll consider is the ONCS problem over a ring R. So given three matrices defined over the ring, you want to ask whether there's a vector in the ring, a vector Z, which satisfies AZ times BZ equals CZ. And now, typically to make these succinct arguments, the prover is going to, make a cryptographic commitment to the witness Z. And in order to give us the infrastructure to do that, I'm going to talk about what a bilinear module is and what that means. So our scalar product arguments are going to work with commitments defined over these bilinear modules. And for a bilinear module, we're going to have like a left module, which you can think of as being like messages, a right module, which you can think of as being like commitment keys, and like a target module, which you can think of as being like commitments, and some kind of bilinear map, some kind of way of multiplying these two things together. And then if you have this very abstract setup, then basically you have enough structure to define some version of Pedersen commitments over the modules. And you can do things like run Schnorr protocols over these modules. And then, given that we'll be able to give arguments of knowledge for reasoning about things like Pedersen commitments and like more general scalar product commitments over these modules, we'll be able to get an argument about R1CS over certain rings. So whenever we have a bilinear module, which has some kind of extra security properties, and whenever this left message space is also a ring, then we'll be able to get an argument for R1CS over not the original ring, but like a closely related like quotient of this ring. And the prover time here and the verifier time are going to be like linear in terms of operations in all of these modules. So, comparing to the discrete log setting, you can think of protocols which might use like a linear number of group operations. And then the proof size is going to be like a logarithmic number of commitments. And that's logarithmic relative to the size of the R1CS instances. Okay. So I guess this might be a good time to pause and see if there are any more questions about maybe about this bilinear module setup or anything else so far. All right, if there are no questions, I'll just head on. So one of the nice things about having this very general setup with these bilinear modules is that if we just instantiate these bilinear modules somehow, then we can recover R1CS arguments for all different applications. So there are many in our paper, but one of the new ones that we came up with is like a lattice-based succinct argument for R1CS defined over the rings that people use in lattice cryptography. So this would give you some kind of plausibly post-quantum secure succinct argument. So this is really exactly the same theorem as on the previous slide, except I've just changed all the domains and things to be like the rings associated with lattice cryptography and the ring SIS problem.
So how does this differ from other existing proof systems using lattices?
Let's see. So
I guess do Stark's Fry that uses codes, doesn't it? Okay.
Yeah, that's right. So yeah, so Fry uses codes, and actually it doesn't use any hard problems related to error correcting codes.
Okay.
It kind of just uses the distance properties of the code, whereas the difference here is this is more like let's say like a lattice analog of bulletproofs, where you're using hard lattice problems to give you like a cryptographic commitment to a long vector.
Okay, so this is completely new, really.
So well, I guess I guess so. What's new here is that so there was already like a lattice analog of bulletproofs, but just for proving that you knew a message inside a long commitment, but it wasn't really extended to you know, proving different statements like R1CS, for example.
Yeah.
Okay. And you know, it wasn't really in a framework either with the other split and fold techniques. So there were some frameworks, but not quite connected to the sumcheck protocol. But having said that, there are some concurrent works out there. So like there's another cool concurrent work which proves like a very, very similar theorem, basically, lattice-based succinct arguments for NP statements. And there are some other works which they prove like strong limits on you know, just how efficient these things can be. And they have some pretty good and cool instantiations of different lattice rings, which, you know, hopefully are going to lead to some, you know, some exciting and efficient, you know, practically efficient lattice-based succinct arguments.
Oh, there's a question. Maybe I can say it for Kev. Can you explain why I would use this commitment scheme versus IPA as a commitment scheme?
Yeah. So I think Pratyusha's just posted a comment about that, and yeah, I think I basically agree. So
but we should maybe say it for the people watching the video.
Yeah, absolutely. So I'm about to read it out. So Pratyusha says, this is generalization of inner product commitments. This particular commitment scheme is post-quantum. Actually, some of the commitment schemes that we deal with in the paper and that we use for these succinct arguments are like generalizations of the IPA commitment scheme, but just defined over these bilinear modules, so that you can instantiate them in like all kinds of settings, like you know, pairing groups or groups of unknown order, or based on lattice assumptions. So it really should fit in to the same kind of framework. All right, so that's another one of the main results from a paper. And you know, next for the rest of the talk, I'm going to go into a bit more detail about how all of these things work. Oh, I see there's another question. So no gains in terms of communication complexity. So no, that's right. So we have basically we're able to replicate all the communication complexity of other like succinct interactive arguments based on all kinds of different cryptographic assumptions. But actually, based on this framework of sumcheck arguments, we're able to, you know, pretty quickly and easily come up with like lots of new results. So, for example, the generalization of these inner product arguments into, you know, based on different assumptions like lattice assumptions, it's like much easier to come up with once you have this sumcheck-based framework. So we're able to kind of you know, fill in a lot of blanks and like come up with inner product arguments under lots of different assumptions, you know, really quite easily. So no efficiency gains, but like lots of extra combinations that people hadn't investigated. Oh, and there are still some open questions, which come from our work. So firstly, even though some of the sumcheck arguments that we investigate use assumptions based on lattices, which are plausibly post-quantum secure, we still need to analyze the security of sumcheck arguments against quantum adversaries, so like a quantum prover or quantum verifier that might make use of superposition in strange ways, for example. So we're using quantum hard assumptions, but we don't necessarily have quantum security proofs just yet. Another thing we'd like to do is investigate new lattice instantiations from these concurrent works and see how they could lead to different concrete performance improvements from protocols. And using these sumcheck arguments, we were able to capture almost all, I would say, almost all of the split and fold techniques from different parts of the literature, but still not quite all of them. So there are a few. Like the Dory protocol, for example, or a couple of other different works that we didn't quite manage to express as sumcheck arguments. And we're pretty confident that it can be done either in our framework or like a small generalization, but we just didn't quite get that far. So that's still something that's open.
The analyzing the post-quantum security, does it seem like there'll be any obstacle to that, or is it, do you expect it to be quite straightforward?
Let's see. It does seem quite hard. So I think generally the difficulty with these multi-round protocols is that all the split and fold techniques and their knowledge extraction proofs use a lot of rewinding, and it's really difficult to do rewinding against quantum adversaries. There are all kinds of problems with making quantum measurements and stuff like that. So I think it does seem quite hard. But what gives me some hope is that actually people have investigated these things for the sumcheck protocol, and maybe that will provide some inspiration and help with the analysis.
So the best analysis I'm aware of sort of bulletproofs like protocols is the one that uses states restoration soundness. Is it maybe possible to have a quantum analog of that? Because that produces tighter proofs than the techniques.
Yeah, I mean, I guess that kind of thing would be the hope. Yeah, I think it's really interesting, and I haven't really looked into it too much so far, but yeah, I think it's interesting and important. All right, so now let's talk about some of the techniques that we used in our paper. So we're going to start off by talking about how succinct arguments for proving that you can open Pedersen commitments can be expressed as sumcheck arguments. And you can see I've got a car icon on the slide here and a little diagram, and we've actually got a petrol pump, and that's because understanding how sumcheck arguments are connected to Pedersen commitments is really the main part of the talk. And I think if you can understand this part, then you can probably understand most of the following like applications, like modifications, generalizations. So I'll start off by talking about Pedersen commitments and their connection to sumcheck arguments. Then we'll talk about like scalar product or like inner product commitments. So then we'll generalize a bit further up to sumcheck-friendly commitments. Like up to that point in the talk, we'll just be talking about groups and finite fields. So we'll be talking about the same cryptographic setting that like normal Pedersen commitments are defined in. And then finally, at the very end of the talk, we'll generalize just one step further, and we'll talk about how, we'll give some hints anyway about how the protocols can be made to work in like very general rings and modules. And in particular, this lets you see how to come up with like lattice instantiations and how to give succinct arguments based on lattice assumptions. And of course, like I'm just going to scratch the surface here, but there are many more results in the paper, so I'd really encourage you to have a look at it. Okay, so with Pedersen commitments, the common input for the proof and the verifier is a Pedersen commitment over a group, and commitment key, which is a vector, vector of group elements from the same group. And the claim is that the prover knows a message such that when you take the scalar product of the message and the commitment key, you get the original Pedersen commitment. So how do we give a succinct argument of knowledge to show that the prover knows an opening to the Pedersen commitment? Well, what we're going to do, using the polynomials that were given in like the Pedersen commitment example a few slides earlier, the prover and verifier are just going to run a sum check protocol. So the polynomial that we're dealing with here, the polynomial that the prover and the verifier are running the sum check protocol for, is like a product of the message polynomial and the commitment key polynomial. And you can actually take the product of these two because, yeah, again, this is just like exponentiation or like scalar multiplication between field elements and group elements. And so the prover and the verifier are going to run a sum check protocol, and they're going to prove that when you sum up evaluations of this polynomial, you get n times the original Pedersen commitment. So not quite the original one, but n times. But that's okay, because if the prover knows how to open n times the Pedersen commitment, then we can divide by n, and the prover should know how to open the original Pedersen commitment too. So the prover and verifier are just going to run a sum check protocol with these polynomials. And then the one difference from like the classic sum check protocol is that at the end, when the verifier wants to compute an evaluation of the polynomial at a random point, actually they can only open half of it. So the polynomial that we're dealing with is like a product of like a message part related to the message A and a key part related to the key G. And since the message is private and only the prover knows it, the verifier can't compute the PA part of the polynomial by themselves. So the prover has to send this part to the verifier, so the verifier can make a final consistency check. So the communication costs of this protocol are going to be 3 log n group elements. And these correspond to all of the sum check polynomials that the prover sends to the verifier, which are polynomials defined over the group G. And they're all quadratic polynomials, so they all have 3 coefficients. So that's like in log n rounds, log n variables in the polynomials, we've got 3 log n group elements. And the log n plus 1 field elements comes from the verifier's random challenges and this final evaluation that the prover sends to the verifier. Now, the verifier's computation in this protocol is a linear number of group elements. And this comes from the cost of evaluating the commitment key part of the polynomial at a random point. So the polynomial's got n coefficients, 1 for each element in the commitment key. And then when the verifier computes this evaluation, well, that's where all the costs are coming from. So although it's a little bit different, this is actually strikingly similar to the original split and fold techniques. And there's a good explanation of this given in Appendix A of our paper. So, the only real difference at a high level is that, some of the coefficients of the message and the key are like shuffled into a slightly different order. And the split and fold techniques in this 2016 paper actually use a small optimization of the protocol here, so that the communication cost is like 2 log n group elements instead of 3 log n. But still, these protocols are really like really strikingly close. And there's like a good explanation of how this works in the paper. Okay, so next I'll be going into like why this protocol is actually complete and sound. But before I do, are there any questions about this like high-level overview of the protocol?
Yeah, hey, can you just explain again why it's where the 3 comes from?
Right. So so the polynomial that the prover and the verifier are running the sum check on is a product of 2 multilinear polynomials. So in particular, the degree in any variable of this polynomial is 3. And so when you run a sumcheck protocol on this product of two multilinear polynomials, all of the messages that the prover sends to the verifier are going to be quadratic polynomials defined over the group G. And since they're quadratic polynomials, all of them have 3 coefficients. So the communication costs are going to be 3 group elements per round. Now, actually, the split and fold techniques in the 2016 paper are an optimization of this kind of idea down to 2 group elements. And that's because some of the group elements in these quadratic polynomials, they actually depend on group elements that you've seen already. So instead of like sending extra group elements and checking consistency between them using like different equations as part of the sum check, you can actually avoid sending like 1 extra group element per round. And instead of performing like different consistency checks, you can use the same equations to like define the next group element that would have been sent. So it's really a similar kind of thing, but it's like an optimization where you just avoid sending some redundant information.
So you're saying the other direction is also true, that if I want to do a sum check on a product of multilinear polynomials, I can actually do it. I can save like a field element in each round if I do a splitted fold.
Yeah, that's right. So in the original sum check protocol, you could, like, if you wanted to, you could always avoid sending one of the coefficients of each of the prover's polynomials, and instead of doing the consistency checks between different polynomial evaluations and things like that, you could use the same checks to actually come up with like a definition of what the last coefficient should be. So yeah, you can apply the same optimization to the field-based sum check if you want to.
Thanks.
Quick question, Jonathan. So I should think of this P sub A and P sub G respectively as being basically multilinear interpolations of the A and G vectors, right?
So interpolations is another option. You can also do that, but here I'm thinking of each element of the message as being one coefficient of the multilinear polynomial.
I see. Okay, I'll take some time to think about that.
But yeah, I think you can also come up with a protocol that uses interpolations if you prefer. I think.
I see. So you can use any basis, and that's the difference between, say, monomial or Lagrange or some other basis.
Mm-hmm.
Right.
Okay.
Yeah. So so actually, like a reason for going with the multilinear polynomials is just actually to make the connection between split and fold techniques in this 2016 work to get a protocol which was like quite close and like almost equivalent to that one. But yeah, like other bases should also be possible.
Mm-hmm.
Yeah, that might actually relate to something that we've been thinking about for Halo, because the polynomial commitment scheme in Halo is very similar to bulletproofs. So, but part of the expense comes from doing FFTs to convert between Lagrange and monomial basis. So, if it was possible to avoid that and stay in Lagrange basis, that would be nice.
Oh, yeah, sounds interesting. Okay, so next I'll talk a bit about the completeness and soundness of this protocol before going on to talk about some more complicated commitment schemes. Okay, so completeness. We want to know that if the original Pedersen commitment was properly formed, then the verifier is going to accept at the end of this protocol. So what this sum check protocol in the previous slide is checking is that a sum of polynomial evaluations is equal to n times the original Pedersen commitment. And if the prover is telling the truth and this scalar product relation between the message and the key and the commitment holds, then, kind of by hypothesis, we also know that this equality holds here. So in order to know that the question mark double arrow is actually an inequality, we need to investigate the third side of the triangle here. So in order to show completeness, what we want to prove is that this sum of polynomial evaluations gives us the scalar product on the right-hand side. So completeness is basically linked to this claim about like summing evaluations of multilinear polynomials. Okay, so I think this is an explanation of a question we had earlier, I think. So if we sum the products of multilinear polynomials over -1 and 1, then whenever any variable appears with an odd degree in a monomial, then that monomial is just not going to survive inside the sum. It will just be completely cancelled out as part of the sum. So the only monomials that actually make contributions to this sum are the ones which have like all even exponents. And so actually, since we have like a product of two multilinear polynomials, we know that the exponents in the message part and the exponents in the commitment key part just come from 0 and 1. So the only way to get a monomial with like all even exponents is when you multiply the ith term of the message polynomial, like the ith message, by like the ith term of the commitment key polynomial, so like the ith element of the key. And then if you follow logic like this, you can see that like every term used to produce the Pedersen commitment comes up exactly once as part of this sum. Okay, and so considering the triangle on the previous slide, this is enough to prove that the protocol is complete. Okay, so now let's talk about soundness. So the kind of soundness guarantee that we want to prove for our protocol is knowledge soundness. So for knowledge soundness, we're going to have some kind of efficient extractor algorithm that takes as input a tree of accepting transcripts for the protocol and a commitment key and a commitment, and finds a good opening message M, which opens the commitment C. So if our original sumcheck protocol looks like this, then this is what the knowledge soundness extractor algorithm has to deal with, like a tree of transcripts where the top of the tree corresponds to the prover's first message in the protocol. The first 3 branches of the tree, going from like level 1 to level 2, different values for the verifier's challenge. So, and then at each of the leaves, we have like a second prover message. For each of those, we've got like 3 possible continuations with like 3 different verifier challenges and so on and so forth. And so given this information as input, the knowledge extractor is going to compute an opening message M. Right, so what we can prove for the Pedersen commitment is that given a 3-array tree of accepting transcripts for a certain key and commitment, we're going to be able to find an opening. So,
why 3-array?
So in this case, it's going to be 3-array because essentially what we'll need to do is lots of interpolation on the quadratic polynomials that the prover sent as part of the sumcheck protocol. And so, yeah, to interpolate a quadratic polynomial, we're going to need like 3 points at each stage.
I see. Okay, thanks.
So you can think of like the prover's final message. So the final evaluation that the prover sends to the verifier, the evaluation of the message polynomial, is kind of like an opening of a commitment which has length 1. And in the 3-array tree, we'll have 3 to the power log n of these openings of size 1 for this final value that the verifier has. The last sumcheck polynomial evaluated at a random point, which you can think of as a commitment. So we'll have 3 to the log n commitments and openings of messages of length 1. And the general strategy is going to be to operate layer by layer in the tree. And every time we'll reduce the number of openings we have by a factor of 3, but we'll be computing openings which have double the length. And they're an opening for a commitment, which is like, which is a commitment related to the next polynomial up as part of the sumcheck protocol. So we'll go from openings of length 1 to openings of length 2. And you know, so on and so forth, doubling as we move up the levels in the tree. And then finally, we'll get to one single opening of n times c, which is like a multiple of the commitment the prover and verifier were reasoning about. So that's when the extractor will have succeeded in finding like a valid opening message. Because you know, it's an opening to nc, and we can just divide by n to get an opening to the original commitment. So this is the high-level strategy. And if we start zooming in on round I, we're going to see how interpolation comes into play. So what we'll want to show in like the ith step of this argument is that if we have openings for like if we have openings of a particular length for 3 different commitments, which are sumcheck polynomials evaluated at 3 different random points, then we can find an opening which has double the length to a commitment which is like an evaluation of the next sumcheck polynomial up in the sumcheck protocol. Okay, so since all of the prover's sumcheck polynomials are defined in terms of these multilinear ones, we can show that all of them are quadratic polynomials. And it's a 3-ary tree that we're dealing with. So each step in the 3-ary tree, we're going to have openings for 3 evaluations of the ith sumcheck polynomial, qi. Okay. And our first goal is going to be to use these openings of evaluations of the polynomial to actually find openings of coefficients of the ith sumcheck polynomial. And then if we have openings of all the coefficients of the sumcheck polynomial, then using some equations that we know as part of the sumcheck protocol, we can move towards an opening of like the next polynomial up in the tree. And this is going to be like, this is going to be guaranteed by some of the checks that the verifier does. And like every time we do this, we're going to be dealing with like a slightly different commitment key, which has double the length. Okay. So the commitment key at every step is going to be like a partial evaluation of the commitment key polynomial that we used as part of the sumcheck protocol. And so every time you kind of evaluate this polynomial in one extra variable, kind of compresses the number of coefficients in the polynomial by a factor of 2. So this kind of explains why the commitment keys get smaller and smaller as you go down the tree, or like bigger and bigger as you go up. If the 3-ary tree contains like three openings of like different evaluations of the ith sumcheck polynomial, then we can rearrange those using some linear algebra, and we can express like the ith commitment key in terms of like the I-1th commitment key. And then we can rearrange those into openings which have double the length with respect to the I-1th commitment key. And then since we've got these openings for like 3 different evaluations of the sumcheck polynomial, we can interpolate and we can use linear algebra to find openings of all the coefficients. And then, finally, we'd use the equations in the sumcheck protocol to get openings for the next polynomial up in the tree. Okay, so that's how the soundness of the sumcheck argument for Pedersen commitment works. Are there any questions about any of the details here, or how different parts of this would work? Okay, great. Oh, actually, maybe there is one question. Oh, I guess, okay, I guess there's no questions, so I'll move on to the next part. Actually, it's worth saying that, so the procedure here that we had from moving to, you know, commitment openings of like a particular length to commitment openings of double the length is actually, that's actually a general property that we define for like general sumcheck-friendly commitments that we call the invertibility property, which we're going to get to. We're going to get to that for like more general commitments a bit later on. All right, so next we're going to talk about scalar product commitments via sumcheck arguments. Okay, so here for scalar product commitments, the setup is a bit more complicated. The common input between the prover and the verifier this time is going to be a commitment to like a left message vector A, and another Pedersen commitment to a right message vector B. And then finally, a commitment to the scalar product of the two of them. And then actually what it means to prove that you know an opening of this commitment is to prove that you know two committed messages which satisfy some kind of scalar product relation. So this is going to turn out to be like the main building block of succinct arguments for RCS. But anyway, each of the components of the scalar product commitment here basically has the same structure as a Pedersen commitment. So what protocol are the prover and verifier going to run? Well, they're just going to run a sumcheck protocol, which has three different components, but like each of the components of the polynomial is very similar to something that we've seen for the Pedersen commitments. So the first component is a product of two multilinear polynomials and gives you a commitment to the left part of the message. The second component is for the right part of the message. And then the last component is for the scalar product of the two. So this is really, really similar to the sumcheck argument for Pedersen commitments, just with three different components.
And is U chosen in the setup, or is, oh, that's part of the key. Okay.
Yeah. So you can be part of the key. Yeah. So this time at the end of the protocol, the message parts of the polynomials involve multilinear polynomials in A and B that the verifier can't evaluate for themselves. So this time the prover sends those two evaluations, polynomials related to A and B, and then the verifier does a similar kind of consistency check to what we've seen before. And then again, the communication is going to be succinct. It's going to be logarithmic in the length of the message vectors, and the verifier computation is going to be linear because just like before, they have to evaluate different polynomials in all of these group elements. Okay, so completeness and soundness of this protocol is fairly easy to describe. Completeness, to show that the verifier always accepts. Basically, we just need to observe that every component of this commitment behaves exactly like one of the Pedersen commitments we've already seen, and then use like similar kind of reasoning to what we've already seen. And for soundness, this is interesting because qualitatively we get a slightly different result to what we had for Pedersen commitments. So for Pedersen commitments, to get knowledge soundness, we didn't need to use any additional properties. We just needed a tree of accepting transcripts and no computational assumptions. But actually for the scalar product commitments, we need to use the binding property of the commitment scheme. And we actually need to use a 4-ary tree of accepting transcripts instead of a 3-ary tree. So how this argument works is basically to apply the extractor for Pedersen commitments to each of the individual components. And then this is good because it gives you openings for the first and second components of the scalar product commitment. But you don't necessarily know that they're consistent with the last component of the commitment. So this is where the computational assumption and the extra transcripts in the tree come in to allow us to show consistency between the different components of the commitment. Okay. So, it was pretty easy to go from Pedersen commitments to scalar product commitments. So let's not stop here. But before we do move on, I should say that the fact that we can go from this Fourier tree of accepting transcripts to an opening for the scalar product commitment comes from this kind of general invertibility property of the scalar product commitment scheme, which is something we can define and something we're going to see in the next little section of the talk. All right, so next we're going to move all the way up to sumcheck arguments for general sumcheck-friendly commitments. Okay, so just here on the slide, we've got a reminder of the structure that makes a commitment scheme sumcheck-friendly. And so how are we going to give succinct arguments for openings of such a commitment? What will the sumcheck argument look like? Okay, so this time the common input is just going to be given in terms of the, well, just like before, it's going to be given in terms of the commitment and the commitment key CK. And the claim this time is that the prover knows a message which satisfies this like sumcheck-friendly sum of polynomial evaluations from the previous slide. So again, we just have a sumcheck protocol on like the appropriate polynomial given by this equation. And just like in the Pedersen commitment and scalar product commitment cases, at the end of the protocol, the prover sends an evaluation of the message part of the polynomial to the verifier. So the communication costs of the protocol here are the communication costs for the sumcheck protocol and sending the final evaluation. And the verifier's computation this time is computing an evaluation of the key polynomial and one application of this function f, which is going to combine the message part of a final check with the key part of the final check together. So yeah, this f is just coming from the definition of sumcheck-friendly commitments that we had. Okay, so completeness of this protocol just kind of follows directly from the definition of sumcheck-friendly commitments and the fact that every sumcheck-friendly commitment can be written as a sum of polynomial evaluations. And so this is the point for sumcheck-friendly commitments where we define like an abstract property, invertibility for the commitment scheme. And so whenever a sumcheck-friendly commitment scheme is invertible, then we're going to be able to take a tree of accepting transcripts for the sumcheck argument on the previous slide and find an opening message which opens the commitment C. So the high-level strategy is to work inductively, just like with the Pedersen commitments. And instead of using this linear equation solving, which we knew we could do for Pedersen commitments, we're going to invoke this abstract invertibility property at each layer of the tree. Okay, so what is this invertibility property anyway? It's the property that allows us to gradually climb up the tree. And if we zoom in on a particular part of a tree of transcripts, let's say like a k-ary tree of accepting transcripts, then we've got different things in this part of the tree. We've got the ith sumcheck polynomial, qi of x, and we've got some sort of openings of like evaluations of this sumcheck polynomial. And what we mean by openings in this case is that we've got some smaller polynomials, p1 up to pk, which satisfy a kind of sumcheck relation, which is related to the one used to compute the individual commitments, just with randomness in a few of the positions, instead of summing over every single variable. So those are the ingredients for the invertibility property. And what invertibility enables us to do is find a polynomial p, which similarly is like an opening for like a sum of evaluations for the same sumcheck polynomial. in a kind of similar way. And if you like paying attention to the definition of invertibility, what we had in the case of Pedersen commitments was that whenever we kind of inverted or moved up a layer in the tree, we were dealing with openings, messages which had double the length every time. So what that means here as part of our abstract definition of invertibility is that the new polynomial p that we find is going to have an extra variable compared with the original, the polynomials that we started with in like a lower level of the tree. So a polynomial with more variables has like more coefficients, and this is kind of analogous to the length doubling of messages in the Pedersen commitment case. So in the paper, we actually show that lots of different commitment schemes are invertible. So we've got Pedersen commitments, these scalar product commitments, and commitments to linear functions. And as a special case of these, we can show that like polynomial commitment schemes, for example, also have this invertibility property. And we can also run some check arguments on those. All right, so any questions about this notion of invertibility for some check-friendly commitments?
This was definitely the part I had most trouble understanding, but no questions.
Okay.
Does K have to be constant?
Let's see. I haven't really thought about whether it has to be constant or not. I guess if the depth of the tree is logarithmic, then it would be a problem if K was too big.
Right.
It might take too long to gather all the transcripts in the tree. And certainly for all the commitment schemes in our paper, we're considering like constant values of K.
Okay, thanks.
But then I guess, you could be dealing with like a sum check protocol that had fewer variables, and then, probably it would be okay. You could like reduce, right. Kind of have like, maybe a non-constant number of transcripts in every round, but just like a constant number of levels in the tree or something like that.
So it's just the size of the tree has to be small enough, basically.
That's it. Yeah, the number of leaves at the bottom of the tree should be
I see.
Polynomial.
Got it.
Yeah. Thanks for the question. All right. So the last part of the talk is how to generalize from these sum check-friendly commitments, which you could have defined over groups like Pedersen commitments were originally, to commitment schemes defined over rings and modules. And this lets you do things with lattice assumptions and get plausibly post-quantum secure succinct arguments. Okay, so how to move from groups to rings. Everything we've seen so far extends pretty easily to general vector spaces over different finite fields. So we've been talking about Pedersen commitments in cryptographic groups with finite fields, but if you wanted to, you could use bilinear groups, and we can still come up with scalar product commitments to those where some of the messages and commitment keys are in the first source group, and some of them are in the second source group, and then the commitments live in the target group. But how can we go further and get to lattices and groups of unknown order like RSA groups? What we need to do is come up with an abstraction for mathematical structures where split and fold techniques or different zero knowledge and succinct arguments work and have good security proofs. So the abstraction that we use is this bilinear module abstraction that was used to prove like our second theorem about RNCS in very general settings. So the motivation for this is to try and be able to come up with like very general Pedersen commitments. So an R module M is like a generalization of a vector space, but just with a ring R instead of a finite field. And as I mentioned earlier, a bilinear module is going to be this collection of R modules with a left one, a right one, and a target one. And then a bilinear map, which lets you multiply left and right elements together to get target elements. So you can think of messages for a Pedersen commitment scheme being like, somehow like small left module elements, and like the keys of a Pedersen commitment scheme as being like random right module elements, with Pedersen commitments living in like the target module MT. And like as an analog of the discrete logarithm assumption, we've got this kind of bilinear relation assumption. So more explicitly, if we have a Pedersen commitment which is computed like this, we'd say all the messages A come from the left module, the keys GI come from the right module, and then commitments live in the target module. And we've computed the Pedersen commitment by multiplying messages and keys using E, adding them together because we can add elements in the target module. The bilinear relation assumption is kind of an analog of the discrete logarithm assumption with many bases. And this says it's hard to find like a small message A from the left module, so that when you take the scalar product with the commitment key, this is equal to 0. And this is like a generalization of the discrete logarithm assumption, or maybe of a lattices, the cis assumption. And there's a pairing analog of this too. And even if we define this crazy general abstract Pedersen commitment, the sumcheck protocol is still going to work because we're dealing with modules, and you can still define polynomials over the ML, MR, and MT modules. The only real difference from what we talked about already is that messages have to be small somehow in this bilinear module setup. Like for example, in a lattice setting, you can only usually use lattice commitments to commit to like very small message elements. So in order to incorporate these requirements we've got on like the smallness of particular messages, we'll need to put some extra checks into like a sumcheck argument for like general Pedersen commitments over bilinear modules. Right, so the last protocol of the day is sumcheck arguments over rings and bilinear modules. And what we've got here is the same commitment and commitment key as common input, and a sumcheck-friendly commitment over a bilinear module would satisfy the same sumcheck relation. So the commitment would be like a sum of polynomial evaluations, just like before. And the only extra requirement we have is that a message should be short, so that the norm of a message committed to inside the commitment should be less than a certain size bound. So the protocol here is almost exactly the same as the protocol for sumcheck-friendly commitments we've already seen. The prover and verifier just run another sumcheck protocol. The prover sends an evaluation of the message polynomial at the end of the protocol. And as well as performing the same consistency checks as before, the verifier has to do a last check that the prover's evaluation that they've sent has norm less than a particular size bound. Another difference when you want to work over these special bilinear modules and capture settings like lattice-based settings is that you want to use a special challenge space for the sumcheck protocol. Even if we weren't dealing with commitments and we were just dealing with like normal sumcheck protocols over these rings, then it will be necessary to use these special challenge spaces. So please take a look at our paper for more details on these. And in particular, like the bound that the prover checks on the bound that the verifier checks on the prover's evaluations is just a simple bound that you get from working out like the size of the points where the prover evaluates the polynomial and like the size of each element of the message. Right, so when talking about soundness of this final protocol, the difficulty is that when you work over these rings and modules, things are not as nice as they were when we were working with finite fields in different vector spaces. It's hard to do linear algebra over very, very general rings. And the reason is because not all ring elements have multiplicative inverses. And further, we want to make sure that whatever we extract using our knowledge extractor is a message which has a small norm. And we didn't have that kind of requirement with normal Pedersen commitments. So to capture the soundness of this, like this final version of the protocol, we have a generalized definition of invertibility, which deals with relaxed openings. And what a relaxed opening is, for example, for a Pedersen commitment, is it's an opening of like not the original Pedersen commitment, but like a multiple of the original Pedersen commitment. And if the prover's message was supposed to have norm less than b, then it could be that the knowledge extractor can only find an opening message which is still quite small, but just has a bigger norm than what the honest prover started off with. So there's this gap between what the honest prover uses and what the knowledge extractor can get. Now, when working with lattices, we kind of instantiate the bilinear modules with different rings from the lattice settings, and then using some of the results in our paper, we'll spit out different values which tell you like how big the gap is between what the knowledge extractor can do and what the honest prover uses. So in particular, if the honest prover started with a particular Pedersen commitment, then the knowledge extractor is going to produce an opening to the same Pedersen commitment, just like multiplied by like a big power of 8 or something like that. And unlike in the finite field setting, in the lattice setting, you can't necessarily divide your openings by 8 and still have like a good opening of a Pedersen commitment. But we gave a very general analysis in our paper, and these two concurrent works are much more focused on the specific case of lattices, and have like much more efficient analyses in their papers. Okay, so a last thing that you might be wondering about is, well, if we can only deal with relaxed opening to Pedersen commitments, how can we actually reason about like R1CS and like general statements? Like, wouldn't we only get a solution to like a relaxed R1CS instance? So we can get an exact R1CS instance. We don't have to worry about getting like a an approximate R1CS solution or something like that. And the reason for this is if we get a relaxed opening for a certain Pedersen commitment, then you can see this as like I don't know, like a strange fractional opening of the Pedersen commitment. The issues are that a fractional opening is not necessarily the same as a real one. This factor that we want to divide by to get the fractional opening might not even be invertible in the ring. It might not be like a small message, so it might not be a valid opening for that reason. So the way we fix this issue is by working with R1CS over like different quotient rings in which this fraction actually makes sense. And by interpreting all the commitments in their openings over this quotient ring, we can deal with the fact that we can only have like relaxed openings to Pedersen commitments, and we wind up with like exact witnesses for R1CS statements over these special quotient rings. Okay, so here's a quick list of what we can actually do with all of these bilinear modules. We can handle the discrete log setting, settings based on pairing assumptions, groups of unknown order like RSA, and the ring cis setting uses lattice assumptions. Okay, so this brings me to the very end of the talk. Let me summarize our results. Our first result was to show that actually to get succinct arguments of knowledge for sumcheck-friendly commitments, you can run a sumcheck protocol. Our second result was that in this very general bilinear module setting, you can get succinct arguments of knowledge for R1CS over quotient rings with logarithmic proof size. And as a corollary, we've got a succinct argument for R1CS based on lattice assumptions, which is plausibly post-quantum secure. So the takeaways here is that we've got many sumcheck-friendly commitment schemes out there in the literature, and split and fold techniques for these can be viewed as sumcheck protocols. And lots of the different cryptographic settings that we're used to are actually like special cases of this, like bilinear module formalism. So that's the end of the talk. Yeah, thanks very much for listening. And if we've got time, I'd be happy to answer like any more questions that people have.
So for the lattice instantiations, how does the concrete efficiency of your protocol compare with LA21 and ACK21?
Let's see. So, so I would say that, okay, so I'll compare to ACK21 first. So ACK21 uses the same kind of lattice instantiation with like, you know, a similar choice of a ring. So like, you could say it has like the same choice of bilinear module. Actually, we ought to get comparable efficiency to the results in that paper. I'd say the difference between, you know, the statements in our papers is really, you know, we have kind of less efficient looking statements, but the reason for that is because we were doing like a very general analysis, which tried to capture like these four different settings at the same time. And then because of that, we weren't necessarily able to make use of like, you know, special facts about the challenge spaces and different things in the lattice setting, which give you better bands. So with a tight analysis, we ought to get the same kinds of efficiency as ACK21. LA21 is a bit different because they actually have a like a different instantiation of bilinear modules with like different rings and different lattices that they can use. And those have some like really advantageous properties. So we were talking about like relaxed commitment openings where you can only open a multiple of the commitment that you started with. But in the setting that's used in LA21, they can actually get like more exact openings which don't have this multiple. And that's the kind of thing that would really improve practical parameters once you did the analysis.
Thank you.
So I suppose one question to ask, given that you were on the original split and fold paper, how much was that the split and fold techniques actually inspired by the sumcheck protocol?
I don't think it was at all, actually. I mean, at least it, you know, it wasn't in our mind at all when we were thinking about the protocol. There's this other paper called something like linear algebra with sublinear zero knowledge arguments by Jens Groth, and I think mostly when we were thinking about this original split and fold paper, we were looking at techniques from that paper. Now, you know, those techniques, you know, perhaps they were in some way inspired by the sumcheck protocol, but I would have to ask Jens about that because you know, he wrote that paper all by himself. But I think for the 2016 one, we were just thinking about this 2009 paper.
Right. I mean, so looking at the people that started applying split and fold to multilinear polynomials, the connection became a lot clearer. You know, a lot more obvious.
So sorry, could you repeat that? So
basically, sort of when I read papers like Dory, it then became very clear that they were doing something somewhere in between sumcheck and split and fold.
Yeah, right. Yeah, I think another thing that possibly makes it more difficult to see the connection is that the split and fold techniques are all written, you know, they're often written in this like recursive way using round reduction. So you just see two rounds of the polynomial at a time. Whereas like I think it's a lot easier to see the connection if if you write down like the full split and fold protocol as a loop, then yeah, I think it becomes much more obvious.
Jonathan, asking a question for Alan in the chat here, which I think you may have touched on earlier in response to a question from Dara. Is Fry a special case? That's from Alan.
Let's see.
Maybe for anyone watching this, at Fry is F-R-I, like not the word fry, like turkey frying.
Okay, so yeah, I think that's a great question. That's not actually something we've investigated so far, but you know, I think it's quite plausible that you know, Fry does have some connections to the sumcheck protocol. Possibly might be a little bit different from some of the other sumcheck arguments here, because you know, Fry's really presented as an IOP, and then the cryptographic commitment scheme there is based on like Merkle trees and hash functions, and doesn't have like quite the same homomorphic properties. So I think there's probably a connection to, you know, the original sumcheck protocols, like, you know, almost certainly, but like whether it's directly connected to sumcheck arguments, I'm less sure because of the cryptographic commitment scheme that's used.
Great, thank you. And thank you very much for your time today. I know I want to be respectful of it, and I know we're about out of time for our session. Does anyone have any closing questions before we conclude?
I would say that, like, if anybody does have any more questions, but they're worried about time or they need to go, then you know, you feel free to, you know, send me any questions by email. So my email address is jbt@zurich.ibm.com.
What's the next step? What's the next generalization?
It's a good question.
It's a very open question.
Yeah. Let's see. I think for now, I'd just like to try and capture like the remaining few split and fold techniques that that we didn't fit into the framework in our paper. So you know, like Dory, for example, and we do have something that works over RSA groups, which is similar to the polynomial commitment scheme in the dark paper, but not exactly the same as it. So I think for now, I'd just like to improve things slightly and just capture those last few split and fold protocols.
Cool. Thank you.
Awesome. Well, thank you very much, Jonathan, for presenting, and you know, thank you, Katerina, if you're still in here, for your work on this paper. And I'm going to go ahead and stop recording. Thank you to everyone in the audience who attended, and we'll look forward to seeing you all next time.